Hello everyone, this is Mr. Appel, and today we're going to start talking about probability. Hooray! So let's get started. So some language, some vocab you need to be familiar with. When we talk about an experiment, that's just anything you do when the outcome is uncertain. So rolling a die, flipping a coin, things like that are examples of experiments. Not scientific experiments, but math experiments. Some overlap there, but anyway. The sample space, that language is really important in probability. The sample space is a list, a set of all the possible things that can happen in an experiment. So for example, when you roll a die, the sample space is the set of all of these numbers. 1, 2, 3, 4, 5, 6. That's the sample space, because those are all the possible examples. An event is what happens. So when you roll a die, what happens? You might get a 4. That would be an event. So a subset of that sample space. So that's some probability vocab. So just as an example, I roll a die. The event might be a 4 or a 2 or a 1, but the sample space would be the set of all the possible outcomes. So the size of the sample space would be 6, because there are 6 items in that. When you roll 2 dice, you might get a 3 and a 5. So there's 2 elements to the event. The sample space is a little bit more involved. The sample space is all the possible outcomes. So you could have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. And those are actually different outcomes. If you think of these as 2 different dice, like a red die and a green die, a red 2 and a green 1 is different than a green 2 and a red 1. So there are actually 36 different possibilities. 6 times 6 is 36, 6 for each die. When you roll 2 dice, there are 36 different possible outcomes. And if you don't totally buy that, we'll take a look at that at some point in the near future. So one thing to think about, how many simple events are in the sample space of rolling 2 dice? So simple event, simple event is roll a die. Another simple event is roll the second die. So there are 2 events happening here. And they are mutually exclusive events. They don't want rolling the first die, the green die, has no impact on what happens when you roll the red die. So that's what we mean by simple events. They don't impact on each other. And that's going to be an important idea as well as we move forward. Okay, so just as an example, very basic probability. You roll a die. What's the probability of rolling a number less than 4? So the probability, this is some notation that we use. The probability, this is the event, in this case getting a number, less than 4. So that's the event. And what we do is we write the number of ways that the event can occur out of the total number of things in the sample space. So how many events are there that satisfy this criteria that are less than 4? Well, there are 3 of them, 1, 2, or 3. So there are 3 possibilities. What's the total size of the sample space? 6. And so the probability is 1/2. Okay. So some of that notation that I just showed you. So an event might be A, B, or C, or whatever it happens to be. And that capital P in this context refers to the probability. So this right here means the probability that event A occurs. So event A might be getting a 2 on a die, or maybe B represents getting heads on a die. On a die, how about on a coin when you flip it? So that's what this notation is, and if you're not already familiar with that, you'll get more familiar with it as we further our study of probability. Moving on. So 2 different types of probability. So there's empirical probability, which is a probability that's based on observation. So what actually happens when you conduct an experiment, when you actually perform the experiment. And that is different from the theoretical probability, which is sort of what should happen. So for example, if if you have a fair coin and you toss it, it should be equally likely to land on heads or tails. So if you were to toss a coin 10 times, you might expect that there'd be 5 heads and 5 tails, because there should be 50-50. But of course, if you actually toss a coin 10 times, that's not necessarily going to happen. You could get all 10 heads, You could get all 10 tails or any other combination. So the empirical probability would be where you actually conduct an experiment and then use the experimental data, use the data that you collect to make predictions. The theoretical probability is when you know, for example, that, let's say rolling a die, you know that it's a fair die, you know that each of the numbers 1 through 6 are equally likely, then it's simply the number of ways it can occur out of the sample space, like what we just did in that previous problem. It's important to make a distinction between theoretical probability, which is what should happen, versus empirical probability, which is what actually happens. One quick little note here is a probability must be between 0 and 1, including 0 and 1. Right? An event can be completely unlikely to happen, means there's no chance, which would be a probability of 0. It can be certain to happen, which would be a probability of 1. Right? So if I said, what's the probability of rolling a number on a die that's less than 7? Well, how many ways can the event happen? There's 6 ways that can happen. 1, 2, 3, 4, 5, and 6. They're all less than 7. And the number of outcomes in the sample space would be 6. So that probability is 1. And I think you'd agree this can't possibly be bigger than 1. Right? You can't have something happen more often than there are possibilities. Wow, I said that really badly. Let me try that again. So if you're rolling a die and there's 6 possibilities in the sample space, there aren't 7 different possibilities for what could actually happen. So this number, the numerator, can't ever be bigger than the denominator, so the probability must be no bigger than 1. 1 being certain, 0 being impossible, and then anywhere in between. Sorry, that was wordier than it needed to be, but so it goes. Complementary events. So we use this notation, I don't know what to call that, maybe a complement, I would read that, A and A complement. So if A is some event, a complement would be the probability or that thing not happening. So for example, if we were picking cubes, colored cubes out of a bag, you guys like that example, colored cubes out of a bag, you were interested in the probability of getting an orange cube, right? So there might be some probability of getting an orange cube. But if you then were interested in the probability of getting a cube that was not orange, that's the complement of that set, because something is either orange or it's not. That covers everything. So if you say, what's the probability of getting orange or probability of getting not orange, those two have to add up to certain, because it has to be either orange or not orange. There's no other possibilities. So this idea that the probability of something happening plus the probability of it not happening must equal 1 is useful, because sometimes, and you see if we rearrange that equation, we could say the probability of getting orange is 1 minus the probability of getting something that's not orange. There are a lot of situations where calculating the complement of the event, calculating, for example, that it's not orange, in some cases might be much easier than calculating the probability that it is that. And so we'd use the complement to help us calculate the probability of an event occurring. So that notation, that language about complementary events is going to be important. Okay, one more thing. Actually, you know what? I think we're going to stop right there, and we'll come back and pick this up again in day 2. Hope you enjoyed this. Have a great day.